Okay, so let's continue. So just to kind of go back to this lecture, right? Basically on queuing models. And you see that, right? Queuing models rely on the properties of the exponentials, right? And the most important properties is the memoryless property, right, of the exponential, namely that, right, if you have waited for a certain time t, condition on that, right, the probability you wait until an extra amount of time h is the same as if you have not, right, waited. Like the conditioning doesn't matter, right? So, and this, right, of course, can be called the renewal property, meaning that after you've waited a certain time, it's as if you have not waited that amount of time at all, right? And that's crucial, right, to help us simplify, if you will, right, queuing models. Because, right, when queuing models, after a server is finished, right, then the person in the queue will come in, right, to fill in that server. And it will be terrible, right, if we have to update, right, the remaining times of the remaining servers depending on when and where as in the server, right, which server that new customer in the queue comes in. Okay. Now, I'm not saying that that's not possible and that would be more realistic, but the tractability of the model, right, will be really low, or well, I don't know, right? Basically, the computation requirement will be quite high if you have to like really update the remaining times as no longer, right, the original model, which is exponential, or something else, and keep updating, right, every time, you know, a customer finish, right, and then a new customer comes in to fill in that server. And so, right, um, the recap, right, of the exponentials, right, are as followed. And so, by the way, right, this lecture has been kind of rewritten a bit substantially. So the new slides have been, posted, right, on Canvas. So what you are seeing here is not the same as what I said before. I mean, it's essentially still the same content, but I'll point out, right, it's just reorganized, and there was one mistake that I made last time that I want to point out. And so basically, right, the story is still the same, that if you have like independent exponentials, right, with different rates, and the minimum, right, is the variable of interest, because, right, the minimum exactly, right, think of the T1 to Tn as a time that the customer, right, at this end server will finish, right, with their service, right? So 1, 2, right, up to n, right? And there's a queue here, right? Then basically that the minimum, right, of these TIs will be the time, right, the first customer get out of the server, right? And that's, of course, of interest. And also, right, and this is also exactly the time that the person, right, in the queue would come in and fill in, right, one of the position in the server. And the I here, right, the indicator function, this is just an indicator function, right, is the indicator of which server, right, is the one that got finished, right? Because of course, right, the new customer will come in to replace, right, at the customer in the queue will come in and replace at that server, right? I is a random index, right? Because whichever becomes the minimum, right, is I. And so the key, right, is that, well, the where it happened and when it happened are independent of each other. That's basically that's the first result, right? Which is good. Again, right, this doesn't have to be the case. If where the server, right, finish and when the server's finished, right, somehow is correlated, which, right, seems to make sense. Let's say that if you have like a server that is super efficient for some reason, right, then it could be, right, that the minimum always is that person, whatever, right? But here, if they're independent and they're exponentials, then no, right? Okay. And then, right, the minimum, right, the time that the first server will finish turns out to still be exponential, with the rate being the sum. Again, very convenient, because if we're working with exponential clocks, right, then this becoming exponential is super useful. Okay. Right, the probability that the server, right, that finished first is server K, is the ratio, right, of that rate of the server over the sum. Again, right, we talked about this before, right? Yeah, so this one, right, that we talked about that. I mean, we didn't emphasize this, but you know, that's there. Now, the one, right, that is key here, right, and we did use this last time, but we didn't spell it out. Basically, right, the remaining time, right, this is the remaining time, right, because this is the time that the server finished, right, the first server finished. The remaining time of the other servers, right, will still be originally exponential. Okay, so that's basically, right, renewal system reset. Okay, and that this property number 4 here is the key on how you can keep renewing the queue and act it and compute, right, as if, right, is starting fresh. Okay, and the point there is that here it's very, very general, because the rates, right, are allowed to be different rates, right? Where was it? Yeah, the rates can be whatever you want, as long as they're independent exponentials. Which lead me to my error in this part right here, right? So this part was, right, the part where Mr. X is already being served, right, in the server. Mr. Z comes in, right? And then, right, we ask what's the probability Mr. X will finish last. And the answer, right, according to memoryless property, and I still remember that River was the one who, right, mentioned this, is that, right, well, Mr. X has to finish, right, after Mr. Y, which will be, right, the probability of that, meaning that this is a minimum, right, is lambda 1 over lambda 1 plus lambda 2, right? And then Mr. Z will come in replacing Mr. Y, right? And Mr. X still has to finish, right, after Mr. Z. Oh, sorry, after, right? Meaning that Mr. Y is the minimum, right? So actually lambda 2, right? And then the same thing happens. So it's going to be a square, right? Last time we said it was 1/2, right? Square, which is 1/4, right? Remember? And I made a big deal, and I said, well, this does not generalize to different rates. That's where I was wrong, right? This generalizes, meaning that, right, it's just really memoryless property, right? And the memoryless property carries where all the rates can be different, okay? And that's my mistake last time. I want to kind of correct that. So the property, right, the memoryless property is very, very strong, meaning that you can just almost like use it casually, okay? As long as the exponentials are independent, that's it, right? And every time like the minimum of the events happens, then the residual just reset themselves and become independent exponentials again. Okay, so that's what I want to say. Any question about this? All right. Now the second thing I want to say, right, is already said it last time, but in terms of the hazard rate, right, we introduced the hyper exponential, right? But the story was with you know, battery and blah blah blah, right? So the thing is, well, that's an example, right? But right, you know, here is where we constantly use the hyperexponential distribution. So, right, that basically, again, back to the example of a customer in the queue, right? The first customer, right, waiting for the servers, right, to finished, then as long as that customer has not get out of the queue yet, right, then they will face, right, queue, sorry, end servers, right? I think if you have ever waited in the supermarket where, I guess all the checkout line is, right, being served and you have to decide which one or whatever, right? Then you are in this situation, right? Then the future, right, service time, because you don't know which server you go into, will be hyper exponential. So the hyper exponential is what you always face if you're first in queue and you're waiting to decide which server you're getting into, right? So next time you go to a supermarket, remember, right, hyper exponential, kind of fun too, right? Keep that in mind. So that's we mentioned this, but I just want to kind of make that more formal. All right. Any question? All right. So the next one is gonna be the Poisson process, right? So so the plan, right, is that we're gonna talk about this for the first half, right, of the lecture. The second half will be on Brownian motion, right? And so if we don't finish this, well, that's okay, right? We'll try to go as far as we can. So first of all, right, if this is the first time you see, maybe not, but if you formally, right, first see the definition of, let's say, a continuous time stochastic process, then it's very important to point out certain things here, right? This three is a complete description of the Poisson process, okay, in continuous time. By the way, right, what is a process, right? Remember, a process is a family of random variable, right? Indexed by t, but now t is continuous. Okay. And again, right? Well, you see the example here. There's nothing much about the example, so right, it's pretty easy. But don't let this deceive you, or right? There are a lot about this definition that is not obvious. And the key, right, is about the word completeness right here. Complete. Meaning that everything you need to know about the Poisson process is in this definition. Okay. And that's where it would be surprising because, well, there are only 3 lines, right? Why would that be so? But so and I think, right, like I said, the hundreds these days, this is probably not the first time you see a Poisson process. Maybe, well, you see it, but not, you saw it, but not like, formally in detail, but you have seen it. So you have some impression, right? So let's see. Here's the question. From this definition, right, tell me as much as you can about what you can deduce from this definition about the Poisson process. Because if we claim it's complete, right, then you must have a complete picture of the Poisson process. Can you, from this definition? Give me a few things you can say about the Poisson process from this definition. Make sure I'm on, right? Anything? All right. So let's see. All right. So first of all, right, let's write down something here. From here, I claim that the Poisson process is a Markov process. Is that obvious? Is that obvious from the definition? Probably not, right? But that's the first thing. And you see that, right? Being a Markov process is, what do I want to say here? You know, fits right into the context that we've been dealing with so far, right? In this class about Markov chain and all those kind of things, right? So it's a Markov process. Why? From this definition. Second, right? I guess the well-known picture, right, of the Poisson process as a function of time, right? Meaning the path, right? Something like this. So, right, and so on. Correct? We've seen this before, right? I hope. Now, okay, if you've seen this before, great. If not, this is a typical picture, right, that you will see. Just look up online, right? They'll give you a picture like this for a path of Poisson process. Again, question. How does that come from the definition? Or, right, let me say this. If you look at this and look at the definition, right, at least, is there something strange about this? Or, well, of course, right? You say, well, like you say, oh, of course, the definition says that this must be the case. Anything strange about the picture compared to the definition? So what's strange, right, is, well, if you are to draw something like this in a calculus class, for example, what do you need? Or you need, right, a description of nt as a function of t, correct? You need nt as, okay, one for, like a piecewise function, right? Right, 0, t less than or equal to t1, that kind of thing, right? And then 1, t1 less than or equal to t less than t2, that kind of thing, right? Anything like that here from the definition? No, right? So that's actually the deep part about continuous time stochastic process, right? That it only has a few lines, but from those few lines, right, you have all the things you can say about a stochastic process, right? Here is a Poisson process. And the connection, right, from the definition to these properties are actually something that people would spend time doing, right? And it could be swept under the rug, right? Because it could be technical and more advanced. And so, right, for example, the Markov process is not that hard to explain, but so let's explain it, right? Well, so notice that here, the independent and stationary increments are the two important properties that that define the Poisson process, and you'll see that it's the same properties that will define the Brownian motion. The only difference is that, in the Poisson process, the increment is a Poisson random variable, while in the Brownian motion, right, the increment will be a normal random variable. And so, right, basically, at least let's say intuitively, why would the definition give you some idea about the process? Remember, right, the word increment, right, another name for it would be displacement, right? If you talk about position, change, right? So basically it gives you, right, all the possible change, right? Because this is true for any S and T, right? So it gives you, right, all the possible change of the Brownian motion and how the change are connected, right? So for example, it says, right, that the change at a future time is independent of the change of a recent time, as long as the two changes, as long as a 2 times interval, right, are S, T, U, right? The change from U to T compared to the change from S to R will not be influencing each other, okay? As long as the time intervals do not overlap. And then of course, right, within the time interval, you know how the change will happen randomly, stochastically, right? The change will happen like a Poisson random variable. But like I said, right, intuitively that gives you something, but why would it be possible to give you a graph like this or something like a Markov process, right? It's a long deduction. But yeah, so now let's go back to a Markov process, right? Why would it be Markov? Well, it's Markov because of the independent nature here. So for example, right, if you look at NT, right, condition on the history, right, this notation here, right, means all history up to time S. Okay. Well, remember, right, with Markov, what it means is that you must be able to reduce this history to only the present moment, which is somehow you should be able to reduce it to only NS. And if you can do that, then it's Markov. If you can't, if the history has to be there, then it's not Markov, right? But how can you reduce the dependence or the calculation depending on the whole history to just the most present, right? Most recent moment? Well, the key, right, is the increment, because you will be able to break, right? If you look at this as like the present and this is the future, you can break the future into the present and the change from, right, the present to future, right? Or from future to present, whatever you want to say. And there you have it, because, right, this part is independent of the history. That's actually this part right here, because it's true for any RNS before, right, the future T and U. The change, right, of the future actually is independent of the whole past. That's the key, one of the key part of the independent increment, right? The change of the future is independent of all the past history. So this part is independent of the whole history. So condition on this or not doesn't matter, right? Well, this, of course, is just the most recent time, right? The most recent information. So you can reduce this whole thing, of course, to NS. And there we have it. That's Markov property. Do we understand? Any question on this? All right. Now let's try to explain this path a little bit, right? Why would the path be like this? Well, first of all, right, if you look at the definition of the increment, you see that the increment, right, is always non-negative because the Poisson is non-negative. So that alone, right, will tell you that the path will keep rising, right? It cannot fall. Because if it ever falls, right, then that means that the change from the future to the past is a negative number, contradicting the fact that it follows a Poisson, right, distribution. Okay. Now, second, right, the increment, right, can only be integers, 0, 1, 2, etc., right, because of the support of the Poisson distribution. Now, if the change, right, can only be an integer, then you kind of see, right, that if the change is 0, that's a flat, right, line, because there's no change. Change is 0 is no change. And then, right, if the change is 1, 2, etc., that corresponds to the jump, right? But then, right, one thing that is subtle still remains, and we will not address this. Given that, right, the Poisson random variable can take values 2, 3, and 4, etc., why is it that, right, and this is true, that if you look at any Poisson graph out there, or it is true of a Poisson process actually, the jump will only be one at a time. And by the way, right, if I failed to mention it, and I think I did, well, you know, example tells you, right, this, right, the Poisson process is also called the counting process because it starts counting, right, from 0 to 1 to 2, etc., right? And this really represents, right, the number of, let's say, customers coming into the store so far, right? You open your store today at 8 a.m., right? There's 0 customer coming in. After some random time, T1, right? The first customer comes in, so the count goes to 1. After some other random time, second customer come in, third, and fourth, right? And so you kind of can have an inkling here, right? That basically, if the jump is one at a time, what does it mean? We say that there's no double event, right? Triple events and things like that, meaning that customers don't come in pairs. Well, again, right? This is not real life, right? Because I mean, well, customers do come in, couples do come into a shop, or family do come into a store, right? But with the Poisson process, right, that won't happen, or at least you look at, I guess, that as a 1 unit or something, right? But the jump is only 1 at a time. Okay, and it counts, right? It counts up how many events have happened so far up to time t, up to a including time t. No, not including, because yes, including time t. All right. Any question about this? All right. So now, having pointed that out, let's come back to the lecture. Oh, nope. Okay. So the next topic, right, would be the connection, right, between the Poisson process and the exponential distribution. Because you can, well, we did allude to it last time, right? But there we use the exponential as the model for a queuing, right? For a queuing model, right? But like, you know, if you want, right? And I think here, there's this mg infinity, right? M here is for Markov, for arrival. And, you know, basically we say the arrival follows a exponential clock. G is for general, meaning that you don't care what the server time is. The reason is, right, here you kind of have infinite servers, okay? Well, is that been realistic? The answer is no, of course, there's no infinite servers out there. Well, there could be, right? If you have like a lot of servers and you're not worried about like servers being backed up and stuff. But what I want to say, right, is that here that actually describes something like a Poisson process in this way, because right, each customer comes in, there's no queue basically, right? Because each customer comes in will immediately come into some servers, right? Because it's servers infinite, right? There's no backup time. But so if you look at right the number of customers in the server so far, right? Then all you have to do to keep track of the time, right? The inter-arrival time between customers coming into the servers, you know? So, okay, first customer comes in, and then a little bit later, right? The second customer comes in, etc. Right? So you will keep counting how many customers have been in your system so far, because you have infinite servers, so you don't care, right? That would follow a Poisson process. And the exponential time, right, will be the exponential time of the arrival of customers, right? The service time actually doesn't matter because, right? Well, I guess, you know what? I guess it does. Sorry, right? In this way, that the customer, after they finish, right, with the service, they could exit. So when I say you count the number of customers in your server so far, I guess I mean, right, when they come in, you count them as one and you don't care when they exit, right? Because if they do exit, they do reduce the count of the system down. So sorry, I guess I was not being precise, right? When they come in, you count and then that's it, right? You just don't care when they exit. But so you count the number of customers arriving in the system so far, right? That would be a Poisson process. Okay. And so, yeah, but here, right, to make it formal, right, basically, there are two ideas. The first is the arrival time of the nth event, right? So the arrival time of the nth event is basically, you know, whenever, right, the nth customer arrives. Now, but what we care for is the inter-arrival time, the, the arrival time between two consecutive events, right? So in the picture, these are inter-arrival time. And notice they're random, right? You don't know between two customers how long it will take. But right, this moment right here is the S. Okay, these moments are the S. So the only coincidence is T1 and S1 because they're the same, right? But after that, right, the S2 and the T2 are not the same, right? S2 is here, T2 is over here, right? S2 is here, right? This is S2. Okay, this is T2. So anyway, right, the key is that the inter-arrival time are independent exponential, lambda. While, right, the arrival time of the nth event follows a gamma distribution because it's the sum of exponentials. Now again, right, if, right, you feel this is natural because the story we've been telling, pay attention and notice that it's a story, right? Meaning that, well, you know, we said is customers arriving and things like that. Mathematically, all you have to go with is the definition. And so, right, the challenge, of course, is to derive the result from the definition. That is somehow contained in this is the fact that the inter-arrival time is an exponential lambda. Is that okay? And that's the challenge. And, right, so this is just an example where, right, you know, we could calculate the expectation of the inter-arrival time, right, of event here, and the arrival, the expected time of the 20th arrival, right? But yep, the opposite, right, is that if you start from the Poisson, sorry, start from the exponential, right, random variable, what does this mean? So basically, right, you have a moment, right? You have a moment t that you're, oh, I guess the moment here is 1 right here. So you fix 1 hour, right? You fix 1 hour. And between that, right, you count how many customers have arrived. So this is T1, this is T2. Sorry, between this is T2, right? And then this is T3, right? So in this example, right, you have three customers coming, or three events, right, before time one, because T4, sorry, this is so let me say this, right? If I name them like this, then this would be S1, S2, S3, S4, right? That the arrival time of the T1 is a length here, T2 is a length here, T3 is a length here, and T4 is a length here. Is that okay? But anyway, right? Basically, if you sum up independent exponentials, right, that's the S, and you look at the largest F, right, before time one, of course, that's a random variable, right? This is a sophisticated random variable. I mean, not that sophisticated, but if it's the first time you see this, right, you should try to deduce its meaning. It gives you the index, right, of the largest amount, right, that you can sum up the exponentials so that the sum is less than one. Again, right, this amount is random because it depends on what the value of the exponentials come out to be, right? But anyway, this amount right here will be a Poisson random variable. So, right, it goes backward and forward. If you have a Poisson process, then you can define the inter-arrival time, and the inter-arrival time will be an exponential lambda. Conversely, if you have the exponential lambda and you define the count random variable, right, counting the events so far according to the Poisson, the exponential clock, then that count will follow a Poisson distribution. Do you understand? Any question about this? Okay. So the proof, right, of the Poisson distribution is by conditioning on the nth arrival time, right? So basically, if you suppose that there have been n, right, arrivals, right, and at time s, so to have exactly n arrivals here, then first the n plus one must occur after time one, right? So the picture is like this. Here's 0, here's 1, right? Here's Sn, and Sn plus 1 must be here, right? So basically, the nth arrival time is at S, then the next one must push it beyond 1 minus S, the next inter-arrival time, right? This is Tn plus 1. And you can prove, right, by the gamma. I guess you don't have to. The reason, right, is because you have the fact that this guy is an exponential random variable. So this is just a CDF of an exponential lambda, right? But that's conditional, right? This is a conditional probability, conditional on Sn equals to S. So to get the unconditional probability of n equals to n, then you have to take this quantity and integrate against the density of the gamma. So Sn here has a gamma distribution. And then you will uncover the Poisson distribution from this conditional distribution, right? There you go. So you see, right, it's quite technical. And it would use the gamma distribution, which we did not go over in this class, or you probably won't see it. You wouldn't have seen it, right, in a probability class. But, like basically in a statistics class, maybe, right? So what I'm saying here is like, right, all of these actually do follow from the definition of the Poisson process, but to put them together, right, and then establish the mathematics, it's not easy, right? Okay, any question? Oh, so I guess I had that previous slide where I should have taken them away because I had the slide below here that addressed that. Yep. So to explain why the inter-arrival time, right, is exponential, we do something similar by conditioning, right, on the first time of the arrival and looking at, well, what would happen so that, right, the second time arrival is more than t, given the first time is s. Well, if the second arrival is more than t, right, and that means from the moment s to moment s plus t, the count has not increased. It's the same count, right? But then, right, using the fact that the Poisson process is independent, has independent increment, then you can reduce this to the probability, right, of Poisson, right? S plus t minus s is equal to 0. Right here, right? S plus t minus s is equal to 0. Which is, of course, right, it's just Poisson t equal to 0. Do you understand? So, right, again, right, we just basically try to interpret, right, the connection between the arrival time and the count. If the arrival time, or rather the inter-arrival time, is beyond a certain amount, given that the first time, right, is at a moment, that means that there's no change in the count from that moment until the moment s plus t. And exploiting, right, the Poisson property, we can deduce what that distribution is. And by the way, right, the whole message, of course, is that this is a gamma distribution. Sorry, this is an exponential lambda distribution. You understand? Any question on this? All right. So let's skip all this. Now, so that's Poisson process for you, right? So basically, whenever you want to model, right, an incoming stream of events where, right, inter-arrival time is exponential, right, then you can use the Poisson process as a count. Again, right, how many people have arrived so far in a queuing system with infinite server, right? So that, or with an infinite queue, if you will, that's fine too, right? With an infinite queue, so that people don't leave, right? If they see that the system is full, then that will be a Poisson process. Now, but I guess, right, the limitation, if you will, right, of the Poisson process is exactly the fact that it only jump one at a time, right? It only jump one at a time. And so that's by construction, right? That's by its definition. And so you would wonder, well, what if I want to model, right, processes with exponential arrival time, inter-arrival time, but the count, right, could increase by more than one, right? Or it could even decrease, right? Who knows, right? So basically you want this jump right here to be flexible, right? Or to be blunt, you want the jump to be random, right? So basically, you have the exponential clock that tells you, okay, after a certain amount of exponential waiting time, there'll be an event happens, but you don't know how much will happen. Like one customer can come in, two customers can come in, or you can lose customer. I mean, if you allow the change to be negative, right? How would you do that? Well, the answer is actually it's pretty easy, and a compound Poisson process, right, will handle it for you. Okay, and we did mention right before about the notion of compound random variables, right? Remember, a compound random variables is a sum where the upper right limit is a random variable. Remember? And we only mentioned, right, the upper limit as a random variable. We didn't mention what the upper limit has to be, right? Of course, it has to be an integer, right? Otherwise, the sum doesn't make sense. We didn't mention anything beyond that. But of course, like the most reasonable, right, random variable to put for the upper limit will be a Poisson random variable, right? Because the Poisson random variable can take value from 0 to infinity. So that puts no cap, right, on what the upper sum, what the upper limit could be. Now, instead of a Poisson random variable, you put a Poisson process in here. Then you obtain, instead of a compound random variable, you obtain a compound Poisson process. Okay. So a compound random variable, right, is a sum yi, I equals to 1 to n, where n is some integer, right, random variable. But Poisson, right, is a most popular choice. But compound Poisson process, because you have the word Poisson here, is when you use the word Poisson. You use the Poisson process as the upper sum. Okay, so right, yi here, right, exactly represents the jump size. Okay, now why? The reason is very simple, right? If you track this sum as a function of t, right, which is time, you see that, right, the sum doesn't change, right, as long as nt doesn't change, right? Because, well, if nt is 3, the total sum is still whatever that quantity is. But at the moment, right, when nt changes from 3 to 4, right? Suppose nt change from 3 to 4. Then qt, right, change from the sum, right, yi from 1 to 4. Sorry, the sum from 1 to 3 of yi to, right, a sum from 1 to 4 of yi. Agree? So of course the net change there, right, is y sub 4. Y sub 4 is the change of q, right? When nt moves from 3 to 4, then qt picks up a y sub 4, whatever that random variable is, whatever that value is. And so from that point of view, right, qt would jump, but with the jump size y sub 4. Right? Any question about this? Right, and so the expectation and variance, right, of a compound Poisson process follows exactly what we did with a compound random variable, right? So it's use the law of total expectation and law of total variance, right, to calculate it. Okay, so that's compound. So what do I want to say here? That's compound Poisson process, right? Now a hand in hand, if you will, notion of compound Poisson process is something called Poisson thinning. Well, you can call it Poisson thinning, but basically, right? So when you have, let's say, right? So compound Poisson process, right, basically generalizes the jump size, right? Poisson thinning basically look at the jump and assign it to type. Right? So like this, right? Say you sit at your store and you look at customers coming in, right? That's a Poisson process because customers come in, let's say one at a time. But, right, let's say you note that the customer is male or female, right? Let's say those are the only, no children or whatever, right? Then you see that then you're looking at a very different Poisson process than the Poisson process of the customers coming in, right? Because if a male customer comes in, then the process for female customer doesn't tick, right? But if a female customer comes in, then the process for the male customer doesn't tick, right? So you kind of distinguish the event into types. And of course, the easiest one is to distinguish into two types. And then the result is, right, that basically if you do that, then each of them is a Poisson process, right? With the rate being proportional to the original rate by the success probability you assign. Now, of course, right, why is this a flip side of the compound Poisson process? It's a flip side because if you sum up the two sub-process here for the male and female, then you will get the original process end. But you can see that the original process end is the compound Poisson process from the point of view of these two sub-process N1 and N2. Like that. All right. Any question about this? Okay, so let me mention the last variation of the Poisson process, and then we'll take a break and come back and talk about Brownian motion. Yep, right here. Right. So the last so the basic building block, right, is a Poisson process that whose interarrival time is exponential, right? Is IID exponential lambda, and whose jump size is 1. Okay. Now, if you want to generalize the jump or the change, then you can either make the change random, turning into a compound Poisson process, or you can categorize the jump into type, right? Type 1, type 2, etc., up to type K. Then what you have is a Poisson thinning. So that's changing the jump size, right? The change, the space property of the Poisson process. You can also mess with the time property by stating, right? The obvious move is I do not want the interarrival time to be independent exponential lambda, or I want, right, the rate of the arrival to be also a function of time, which makes sense, right? Because customers could arrive, right, with a smaller rate at the beginning of the day, higher, right, toward noon, and then decrease again, right, toward the end of the day, right, something like that. So if that's the case, right, or if you let lambda be a function of time, then you have something called a non-homogeneous Poisson process. Okay, so clear enough, right? Basically, the increment. So it's the beauty of this, right, is that the definition here is very close to the definition of Poisson process, right? Notice that instead of lambda times t minus s, you have the integral from st of lambda r dr. But, right, of course, right? So basically the message is with the right definition, you can generalize things quite quickly. Of course, right? Being able to generalize things quite quickly doesn't mean you will be able to deduce all the consequences quickly. For example, right? A consequence here is that the inter-arrival time are no longer exponential. You lose that, right? And notice losing that is losing a lot because then you don't have this whole closure property of the exponential, like the minimum waiting time is exponential. You can swap, right? Things like that. But right, that's a different story. If you want a non-homogeneous model, then that's what you have to deal with. However, right, the inter-arrival time are still independent. So basically the time between events, right, the time from event 1 to 2 and event 2 to 3 are still independent, right? They no longer stay exponential, but how long, right, one is does not influence the other, right? So for example, this picture basically stays the same. It's the same picture actually. The only thing different now is that, right, you don't know if these guys are exponential random variables, right? Of course, on the picture, nothing changed, right? Because, well, I just draw a line, a segment. But, right, how long this is no longer controlled by an exponential lambda, right? So they will have different rates, and the rate is no long is not an exponential random. Okay, so that's how you can generalize the time dimension of a Poisson process. Any question? Okay, so let's take a 10-minute break here, right? And let's come back at 11:40, right? Which will kind of talk about the Brownian motion, right? And then wrap up the semester, the course. Oh, while I have your attention, just one thing. So the department policy states that the final exam solution will not be posted, okay? Uh, if you want to see the final solution, you can make an appointment, right, to meet with me on Zoom. I guess it's okay. Toward the beginning of the fall semester, right, and I can show you the solution on the meeting, but the solution will not be posted on Canvas. Okay. Any question about that? All right. So let's take a quick break and resume at 11:40. Okay. Okay, let's continue. So is there any question about anything we talked about so far? All right, so the last thing, or I guess, yeah, the last topic, right, we'll mention will be Brownian motion. So again, right, I mean, for one thing is we do not do justice, right, to any of these topics by discussing them, I don't know, right, in an hour. But my goal for this class is to focus very deeply, right, on stochastic, sorry, on Markov chain, right, because I think that's the foundation. And from there, right, you can dig into these more advanced topics, if you will, right, when you have time. Anyway, right, at least we'll try to give you some exposure to this continuous time process and kind of point out their subtlety. Now, the one thing, right, that we want to say about the Brownian motion is that you will hear it all the time. That they'll say that this is a continuous time random walk, or they'll just say continuous random walk. Okay, and probably you want to understand where that comes from. And where it comes from is by a scaling, right, of the symmetric, okay, emphasis symmetric. Well, if it's not symmetric, you can still get a Brownian motion, but with drift. So symmetric random walk, right? The one half on both left and right. If you do that, right, but take a very small, tiny step, right, and you look at the limit of what you obtain there, you get a Brownian motion. Again, right, that's kind of waving hand because, okay, what does a limit look like? How do we take a limit, etc. Okay, but so in some way, you could look at the random walk, sorry, Brownian motion as the random walk, symmetric random walk with very tiny step. And people do that in terms of simulation, right, to obtain some idea of the Brownian motion. Okay. So right here, right, a Brownian motion is a stochastic process with these three properties. Now, take a careful look at this, right, and tell me if you have seen this before somewhere. And the answer is, well, not exactly, right? But you just saw it about an hour ago with the definition of the Poisson process, right? So, as I mentioned, right? So, well, so I guess the language here is stationary and independent increments, but that's exactly what we were saying about the Poisson process anyway, right? But so the difference, right, is that the instead of being the increment being Poisson random variable, then the increment here is a normal random variable. Okay. Now, what do you think would change when we change the distribution of the Poisson to the normal? How would that change? And also maybe more broadly, right? Again, these are questions that, okay, feels kind of weird to ask right now, but trust me, right? These are questions that you should ask to understand these processes. Now, first of all, right, we have Poisson and we have Brownian motion, which is normal. Do you think we can still play this game with any other distribution? Like the increment having, I don't know, a gamma distribution, the increment having a uniform distribution, the increment having, I don't know, some weird distribution, right? So instead of normal, right, or Poisson, is there something else we can do? Because, right, if we can just come up with any new process with just swapping in a new random variable, then you would question why people would just study Poisson process and Brownian motion, right? Why don't they study all the stuff? Any answer there? The answer, right, is that this is not a coincidence. It comes from, once upon a time, us talking about the sum of independent Poissons is Poisson. And sum of independent normals is normal. Right? We talked about this, right? And this is the, or you can say Poisson and normal are the only two random variables with these properties, right? That basically you sum them and they remain in the family. And that's sort of explain why, right? Poisson and Poisson process and Brownian motion are really the two main processes that you study, right, for stochastic process with independent and independent increments, right? Why so? It's just a consistency, right? Basically, I want to point out that you write something like this down. It's not like you just write it down for fun, right? You are responsible for it to make sense. For example, right, xt minus xs, right, equals to xt minus xr plus xr minus xs, right, for s less than r less than t, let's say. Okay? That's true by arithmetic, right? Now, if you say this is Poisson or normal, whatever, this is Poisson, and you say that independent, right? Then by force, this must be a Poisson. Correct? Or actually, let me take it back, right? You kind of declare that everywhere they're Poisson. Poisson, Poisson, Poisson. So if you don't have a closure here, then what you say here is nonsense. For example, right? You could swap this with the word uniform, and immediately what you say is completely nonsense. There's no such process. Because, right, uniform plus uniform is not uniform independently. Do you understand? So the fact that we put Poisson or normal in there, right, are highly significant. They're sort of like the only building blocks that fit for IID increments. No other random variables would fit. Okay. Now, second of all, right, going back to this Brownian motion topic, what consequence do we have when we replace normal instead of Poisson in the distribution for the increment? What do you think? What would change? So remember, right? Increment means change, right? And let's go back to the picture here, right? The reason why, right, the picture of a Poisson path is like this is because the Poisson random variable is non-negative, right? So the change can only be non-negative. The Poisson process can only stay horizontal or move up. But a normal random variable, right? Normal 0 something, right? Here. Normal means 0, right? So a normal would be able to take on, right, both positive or negative value. That means the Brownian motion path, right, starting at 0, will be able to both increase and decrease. But that's not all, right? What else? Well, as I'm pretty sure you have seen this somewhere, right? The picture is too well known, right? You will see something like this. Okay. All right. What is that? Okay, ignore the spike and all those things. Let's talk about the more obvious aspect. This is a continuous path. Meaning, right, you would draw it without lifting your pencil, right? Continuous in the sense of calculus 1. All right. Again, you're like, okay, of course. Not really. Where in the definition that it says the path must be continuous? Tell me. Right. And even in that kind of subtlety, right? Just to point out the subtlety here, we said it's going to be the limit, right, of the random walk, right, as step size being smaller and smaller, right? Okay, but notice, however, the smaller step size is still a discrete step size, right? Meaning it's still a gap. So if you take very tiny steps, it's still a gap. It's not continuous, right? Or let's kind of like, make a comparison here, right? I mean, when you saw a picture on the screen, you think you're looking at a curve, right? Let's say you use a software to plot a curve, or, right? But in reality, we all know it's a bunch of dots, right? The dots is just so close together that we kind of connect it and make a curve out of it, right? So the same thing here, right? But we declare, right, that the path here is continuous. Okay. So first of all, that I would say that, right, that's the part that's glossed over by anyone who studies ground motion, because like, yeah, of course the path continues. Yeah, but why? Okay. The second is a more mysterious fact, and everyone would pause here because I guess this fact is even not easy to comprehend what it means. The spikes here, right, means something. The spike here has a name for it. It's nowhere differentiable. Okay. And again, I'm not so sure how familiar you are with this notion, right? But if you think back on your calculus education, you encounter, right, some quote unquote non-differentiable function that's not differentiable, right? And then probably you just say, okay, whatever, right? And you move on. But if you look closely at those examples or exercises, they are not differentiable at one point. Like I guess the well-known example is the absolute value function, right? Has a spike here, right? So it's not differentiable at a spike, right? But elsewhere, beyond that, it's still differentiable. And the language becomes confusing because I guess your calculus teacher tells you that, oh, the absolute value function is a not differentiable function. That's correct. But by a differentiable function, they mean a function that's differentiable everywhere. So it fails at one point, they call it a non-differentiable function, right? But to be fair though, right, the absolute value is differentiable almost everywhere, right? It only fails at one point. So it's unfair to call it non-differentiable. All right. In fact, right, in more advanced courses, you will differentiate the absolute value function to get the, almost the Heaviside function, right? But it's minus 1 and 1, right? So this is the derivative of the absolute value. Okay. So actually, you can differentiate the absolute value. It becomes a step function. Okay. So the Brownian motion being nowhere differentiable means that it's not the story of the absolute value. It, to be blunt, has spike everywhere. Okay. And you should pause and think a little bit, because how could that be? Because say you look at a picture like this, right? And okay, my picture doesn't do justice, but if you look at a picture online, right, it basically has a spike, but you would be like, okay, but isn't here, right? In between the spike, I get a straight line, however small that is, right? That means that straight line must be differentiable, right? If between spikes, you know what I'm trying to say, right? There's a spike and there's another spike. There's a next spike, right? Between those two spikes is a line. because computer just connects the dots, right? So it must be differentiable there. What's the answer? The answer is no, that's an illusion. If you zoom in into the picture between these two spikes, you'll see a bunch of smaller spikes in between those two. You understand? So the spikes will never stop. There will never be a next spike. There'll always be a spike everywhere. It's nowhere differentiable. And it's not something that you would have seen in a calculus course, because something like that cannot be written down as a formula. Okay, you have to use like infinite sum in a real analysis course to see it. So long story short, Brownian motion is not your good old regular object that you would just study easily, right? Its path property has many interesting behavior that basically, right, it gives rise to the whole subject of stochastic analysis, right? Or stochastic calculus, or Ito calculus. Okay, so there's a Stratonovich calculus. Let's not go into it. But my point being is, right, that's one direction you can take with the Brownian motion. That is, right, that studying its path properties, studying its calculus properties, okay, is very deep. It's really down the rabbit hole, and you can just keep going on and on. All right. And I want to say this, right, in connection to these three little guys right here. And right, never mind, well, that if you don't see or you don't fully comprehend the path properties I was talking about, that's fine, right? Because I just skipped over a lot of things. I was just giving you information. But the one thing that you should appreciate coming out of this, I hope, is the fact that these three items give rise to all those things, right? And to me, that's the most amazing thing. Because, right, the definition encompasses all the consequences. And these three, let's say, rather innocent looking consequent definitions, right? Everyone probably could comprehend this in a couple minutes, right? There's nothing much to talk about. But comprehending the consequences, right, of these three items is a subject of many, many courses, not just one single course. All right, and that's what I want to say. So, and this is in connection with stochastic process, because this class is called what, Introduction to Stochastic Process, right? But like I said, we mostly focus on Markov chain. But to understand stochastic process proper, right, I would say that you want to understand what it is that you're dealing with to begin with, or how it is that you can get a hold on the object that you want to talk about, right? Because if you have no good idea of what you're dealing with, then anything you talk about after that is a bit of nonsense, right? So how to even start describing a stochastic process, to me, is a much more important question to consider than to understand all these fancy properties of Brownian motion and horizontal process. I mean, understand, to know, right? Of course, you can learn them, right, and use them, right, without questioning. But in that sense, you're just applying formulas without deeply understanding what's going on, right? So the starting point, right, of a Markov chain, for example, is a transition matrix, right? And you should appreciate the fact that with the transition matrix, any question can be answered. Isn't that amazing? But right, we spend almost half the class developing all the answers to the question based on the transition matrix. But so the point is the transition matrix gives all the properties of the Markov chain. Just that little matrix. How? Why? Right? Same thing here. These three little definitions give rise to everything you want to know about the Brownian motion or Poisson process. How? Why? Right? That is the, to me, is the amazing thing. All right, but let's continue, right? To see what is in store for us. So this is following Ross. Ross has a notion of standard Brownian motion. Most other texts, or I myself, would just call Brownian motion without even reference to standard Brownian motion. The reason is right here, what Ross does is he allows a scale, right? So the scale of the Brownian motion just makes the variance bigger. So you will see the swing larger. But the basic picture, right, of the spike and everything doesn't change, right? When you scale it up with a sigma or scale it down with a sigma. Okay. All right. Yep. So here is an attempt, right, at the exactly the explanation of the continuity and non-differentiability. Well, how do we do this? Well, by looking at the difference quotient, right? Uh, if you look at the difference quotient, you see that, right? This difference quotient has mean 0 and the variance 1 over h. And the variance converges to infinity. H equals to 0. So this is something, right? This fraction right here. Basically, it says that by the way, right, what is this? This is the slope of the tangent line, right? Rather, it's the slope of the secant line, right? That's supposed to converge to the slope of the tangent line. The variance converging to infinity is telling you that basically, right, the slope of the secant line changes very wildly, right, as the gap gets smaller and smaller. That's the spike phenomenon you see, right? As you get to 2 points to be closer and closer to each other, right, the slope of the secant line fluctuates a lot. And so, right, that sort of gives you an intuitive idea on why, right? Now, of course, this is again, right, this is taken straight from Ross. But in my class, well, when I teach math finance, I go into much more careful proof of why it's not differentiable. Right, this is an intuition, but there are other things you can do, right, to study the path properties. But right, this hopefully gives you some idea. And what's the takeaway message here, right? By studying the distribution, right, mean variance, you can make some conclusion about the path. And that sort of gives you some clue on why on the connection between the three items here. Because the three items here only give you the distribution, right, of the change. But to make deduction about the path, this kind of right analysis is used. Any question? Okay. So the right at each point t, right, the height, right, or not the height, but the value of the Brownian motion has a density, right? It's a normal random variable, so it's a normal 0t, right? So it has that density. Okay. Now, when you look at, right, a stochastic process, okay, the key, or you can claim that you understand or you know the stochastic process if you know its so-called finite dimensional distribution. Which is this right here. Which is this right here. And the key, right, is that the T1 to Tn must be sampled arbitrarily. Meaning I sample any T1 to Tn, you should be able to give me the joint distribution of these guys. Then if you can do that, then I would say that, right, you have completely described your object, your stochastic process. Now you think about it, right? This is what we call the path probabilities in Markov chain. Remember, we calculate probability, right? X1 equals to something, X2 equal to something, or we calculate the probabilities it avoids certain area getting absorbed by certain time. That exactly are all variations of this question. Okay, and so that's that exercise right there. Now, so the test now, not that you have to, right? Not that you have to really go into this description, but it's something good to keep in the back of your mind that if you look at a stochastic process, right? And if you cannot tell how its different values at different time behave together. And by the way, right, what's a good analogy here? A good analogy here is a stock price. I mean, a stock price, not Bryan motion, but you can use that as a tool for thinking, right? What would a trader or someone who invests in stock, right, want to know about the distribution of the stock, the future stock, right? Well, clearly they kind of want to know how the stock will behave on a certain day, right? Like the distribution of it, what kind of random variable would be. But when you think about it, that's not the only thing, because that's just a single day. They do investment over a period of time, correct? So they want to know, let's say, right, over certain spread of days, how do the stocks behave together, correct? Because based on the joint behavior of the stock prices on those days, by joint here, we don't mean the joint of different stock prices. It's the same stock, right? Like Google, but on different days. When you have the joint distribution of the Google stock on different days jointly together, then you may be able to form, right, an intelligent investment strategy based on this joint distribution, correct? And the key, right, is that you should be able to name any day you want. I want this Tuesday, next Monday, next Wednesday, whatever, and be able to come up with, or be able to pull out, right, the joint distribution of those days. You understand? Right? If you cannot do that, then you cannot claim you understand the stock, or you cannot claim that you have a complete model for the stock price. Yes, is that okay? So that's a finite dimensional distribution concept. And sorry, any question about this? And right, having defined that, then the rest is just technicality, right? How have you come up with that, right? It's a exercise you can do by yourself. And what is that exercise? That exercise is again to test the sufficiency of the definition. Again, right? I think I have probably sound like a broken clock by this time, right? Meaning that I keep repeating about this definition, right? But the reason is because it's so important, right? The whole point of the finite dimensional distribution, right, at least in this context, is to test the sufficiency of the definition. Again, right, if the definition is any good, I should be able to write down the finite dimensional distribution from the definition. Right? If I claim that the Markov chain description by the transition matrix is any good, meaning it's sufficient, then I should be able to calculate any path probabilities based on the transition matrix. And you see, we could, right? We have come up with, I think, all scenarios imaginable and write down the transition, the probability for those paths, right? So that's the point. But once you recognize the significance of that, then the rest are just, really, how to say it's technicality, right? What you do is you exploit the independent increment property to, instead of writing the distribution of the points, you write the distribution of the starting point and the increments. And because they're independent, you can reduce it down to something like this. All right. So maybe not a very attractive object, but let me pause here and see if anyone recognizes what this object is. There's a name for it. Do you know what that is? Well, the name for this is called the joint normal or the multivariate normal. Oops. Distribution. Okay. And anyway, joint normal distribution, multivariate normal distribution is actually very important. You see it used as a model everywhere. If you do linear regression, you more or less deal with multivariate normal without mentioning it or with mentioning it, depends. But it's there, even in linear regression. And in high course in statistics, like variance analysis, ANOVA, that kind of thing, I think, joint normal distribution, multivariate normal is kind of like a given, right? So long story short, the finite dimensional distribution of a brane motion is a multivariate normal distribution. Okay, any question about this? And then from there, right, you can figure out the conditional distribution. So the conditional distribution, right, for the brane motion given, right, a future point is like this. All right, again, right, you're like, what the heck? What's the point? The point is, right, so again, blink and you may miss it. But suppose, right, if I swap this question, suppose for t bigger than s, I condition on xs equals to b. What would this be? Can anyone tell me? If, right, I condition on the past, which is the more natural direction here, right? S is smaller than t, condition on the past. Then the future will behave like a normal random variable with the mean being the past value and the variance being the change between past and future. The time length that has passed. So it's very easy. And this uses, right, what does this use? This uses the independent increment. Why? Because xt, right, is, like I said, right, this is the old trick. This is the trick that you use a lot in analyzing process that has independent and stationary increment, right? Break the future into the past or the present plus the change. Well, what do I know? I already know that the past is b, right? So that's b. What do I know about the change? The change is a normal with mean 0 and variance equal to a length of time. So there you have it. Okay. Any question? So what's the big deal? The big deal here is actually the reverse. Here you condition the past on the future. All right. So it's like this, right? You have a brane motion path, right? So say here I'm at B at S. So I'm asking from here, how would my future position be, given that that's where I come from? That's the second question that I just wrote down. The formula talks about the brane motion. You know that it will end up at a position B somehow. But given that, you wonder where you come from or whatever at S. That's a much harder question. And that requires this sort of like multivariate joint distribution to figure out. It's just, chasing a formula really, right? But why is this significant? it's significant because this is connecting to, right, other topics like for one, right, it's called the Brownian bridge. Not that we will cover this in this class in any way, but Brownian bridge is a topic that is very important. Uh, Basically, it's like a clamp Brownian motion, right? Because if you look at this, right, you have a Brownian motion that will start at 0, so that's definitive. That's a point that's clamped, and then it will end up at a point B, right? So you have a object that moves, fluctuates, but somehow it will start at a point and end at a point. And that object, right, has a very, very interesting distribution that you can use for a certain kind of application, right? And well, again, blink and you might miss it, but you also would have seen this sort of conditional distribution in, let's say, a linear regression class, whether you explicitly mention it like that or not. The reason, right, is because you will have occasion to, let's say, condition on knowing some values of some coordinates that you regress on, or knowing some value of some coefficients of the regression, and you try to figure out the distribution of the remainder of the coefficient of the regression. And if I remember correctly, that's some kind of like conditional normal distribution. All right. So yeah, it's not like I'm trying to say that Brownian motion has any role to play in linear regression. I'm not saying that. I'm saying the same underlying block between the two subjects is the multivariate normal distribution. It's a building block for both kind of topics, but of course they each do their own thing. Any question about this? All right. And yep, right here, if you want, right? This is exactly regression right here. Linear regression even, right? You see that, right? Condition on the future point being B, then the current point on average is a linear function with slope S over T. I mean, actually the T is being fixed, right? So it's actually a linear function with slope S or whatever. So that actually, right, is the linear regression for you, because the conditional expectation is a linear function of what you condition on. That's exactly linear regression for you. Again, right, too much to go into, but check back on any kind of linear regression context and you'll see something like that. Conditional expectation equals to a linear function of, whatever you're regressing on. All right. So here, just a kind of like a fun example, right, to demonstrate the concept of Brownian motion. Not that I think this example exemplifies the use of Brownian motion in any way. The context you would see this is something like a Black-Scholes model. For the stock price. Actually, well, we have 5 minutes left, so maybe let me just tell you something about that, as to me, very like on point application, right, of the Brownian motion rather than this example. So the Black-Scholes model for the stock price will be like this. ST for the stock price at time t will be S0 e to the mu minus 1/2 sigma square t plus sigma WT, where WT is a Brownian motion. All right. So you ask, or you should ask, why is Brownian motion appropriate, right, for stock price model? And that's a very relevant question, and well, explains, or at least, right, requires you to understand the Black-Scholes model. But I would say, right, the first thing is, right, this one, if you study it, will be a generalization of this model. So this part right here is the regular part of a saving account with rate mu. So it says that the stock price is like, it has a growth rate, right? Mu. But then due to the action of, trading and things like that, right? It has a stochastic part that makes it random. And the stochastic part, or the fluctuation part, is modeled by a Brownian motion with a scale factor sigma, which actually corresponds to the concept of volatility. Okay, how volatile the stock is. All right, based on the trading, based on the stock. Okay, that still doesn't explain, right, why Brownian motion is appropriate. But then this will take us into the territory of stochastic calculus. But if you do stochastic calculus, or if you learn it, one thing that you will learn is something like this. We can deduce from this model that DST, which is the change of the stock price in a very small length of time, will be mu dt plus sigma dwt. And this is, right, this comes from stochastic calculus, or Ito formula. But this encapsulates the choice of the Brownian motion, because if you look at the change of the stock, which is the ST, normalized by how high the stock price is, this is called the percentage change, percentage return. So it basically, the return of the stock, right, has rate mu. Again, that rate mu that you see. And then this part right here, right, is exactly the fluctuation of the trading activity. Because remember, right, dwt, the change of the Brownian motion, has mean zero. So on average, it doesn't really change the rate of return. But the fluctuation, right, scales with time, scales with the length of time, and scales with the volatility parameter of the stock. And so this, right, exactly explains the appropriateness, if you will, right, of the Brownian motion in this. And of course, right, other things will come in. For example, this will also, the stock price will also inherit the nowhere differentiability of the Brownian motion, the spikiness, right? If you look at any stock price in the market, you see a bunch of spikes, right? Is that a good thing? Absolutely. Why, right? Because differentiability actually represents predictability, right? If you know the derivative of a path, then you can predict where it's moving in the next instant of time, right? By using the tangent line. And stock doesn't do that, right? You could know that it has been rising, but next moment it could just fall, correct? So unpredictability at any moment of time you think about is actually non-differentiability. Okay, so all in all, right, the Brownian motion is a very appropriate model to use for a stock price model. The Brownian motion is a very appropriate model for stock price, right? And so that's a short introduction to Brownian motion, right? If you will, right? It doesn't scratch any surface, but hopefully, right, can make you guys interested in learning that in more advanced courses. All right, so this is it, right? Exam is from 9 to 12, right, on Wednesday. And you have the whole 3 hours. There's no pre-exam meeting, anything like that. And yep, have a good rest of the summer.
Thank you, Professor.
Thank you,
Yep.
Professor.
Sure.
Professor,
Hmm.
the announcement said the exam was from 10 to 1. Has that been
Oh, I
revised?
apologize. No, it has not. I misspoke. I deeply apologize. I just spoke out of my pardon me, my ass. It's 10 to 1.
Okay.
Sorry. No. Thank you for
So it's still
correcting.
like from 10 to
Ouch.
1 on Wednesday,
No,
correct?
no change, no change. What I just said is a slip of my mind. It's 10 to
Okay,
1.
so it's still 10 to
I meant
1.
to,
And
I meant to use the exam time. I meant to say the announcement. Somehow my mind lapsed. Sorry about that.
gotcha.
Yeah.
Okay, no worries. And all we
Yep.
have to do just make sure is that we show everything on the camera so we don't like receive 0 credit, correct?
Yeah, and I know that, right? That has caused some questions. But like I
Mm-hmm.
said, that is there as a cautionary clause. Like I'm not
Mm-hmm.
out hunting for people violating every little detail and give them 0. But
Mm-hmm.
there have been, like cases, right, where we want to have something on our side to make a case, right? So,
Mm-hmm.
like I said, if it's a like slip and you missed something, I'm not gonna say, "Aha, gotcha," right? But
Mm-hmm.
consistently doing this is a sign of something else. Does that make sense? So it's meant to,
Yeah.
yeah. So if it should not put any burden in your mind, right? If anything, please kind of just take some extra precaution to show everything. That's all. If you're not
Mm-hmm.
doing anything weird, I think I can tell. Trust me on that. I'm not out catching people. That's not my job. I don't want to do that, right? So don't worry. Is that okay?
Okay. Yeah, no, that makes sense. Thank you so much.
Sure.
Have a nice day, Professor.
You too.